Thank you all for your attendance. The LunchMAR talks have been really interesting, and I'm glad to be part of that crowd now. I hope my talk is as interesting as the previous ones. Let's see, there we go. Before I start, I want to thank a bunch of people that have been instrumental in this work. First and foremost, Brian Hudson, who was the pioneer in isotope tracers at Livermore Lab. I want to thank Jean Moran. She's now at CHU East Bay, but she used to be at the lab until just before I got there. We're still collaborating a lot on water projects across the state. Brad Esser, Mike Singleton were my mentors at Livermore when I started as a postdoc, and Brad has retired, but Mike's still around and going strong. Richard Bibby, Stephanie Bibby, and Amanda Deinhardt have been instrumental in the development of our cosmogenic isotope tracers. And I'll talk a little bit about those. And finally, Eric Erder is our eco-hydrologist and light stable isotope specialist. I've had a fortunate to work with a lot of students over the years, thanks to Jean and other professors who were willing to send their students to our lab. It's been great to work with them. And I also need to thank all our sponsors and collaborators, particularly the water boards, John Borkovich, Scott Seifried, and Dory Bellin. They've been supporting our work and providing us with great ideas to research topics to work on, as well as all the people or the water districts and well owners and landowners that we've been working with for their expertise and access to their facilities. And finally, some UC collaborators and the USGS California Water Science Center for their involvement in their leading of the Priority Basin program, the Gamma Priority Basin program. It's been an incredible resource for isotope analyses. A lot of the analyses were performed at Livermore, but the program was run by USGS. So Livermore has a long history of noble gas and water research. It started around in the late 60s with the first noble gas analyses for nuclear test diagnostics. Livermore is one of the nuclear labs of the Department of Energy. Many of the nuclear tests were performed below the water table, and to diagnose the isotopes that were produced, they needed ways to sample groundwater and perform these isotopic analyses. Well, that was a lot of work for about 20 years, and then in the late 80s, the Nuclear Test Ban Treaty was on the horizon. So Brian Hudson had the great idea to use the same technology that they've been using for nuclear test diagnostics, but then for more peaceful applications like tritium-helium dating or tracing groundwater using xenon isotopes, for example. That expertise has continued at the lab, and it's still, I think, one of our unique capabilities. There are more labs that can do tritium, helium, but we try to continue to push the limits of the suite of isotopic tracer tools that we have. As I said, a lot of our work has been funded by the Gamma program from the water boards, and we're now continuing that tradition, trying to develop a well vulnerability decision support tool. So with that, I want to continue that great tradition of asking the audience some questions. And the first one is, which of the objectives do you think are most important for managed aquifer recharge studies? And I've listed a number of possible options. And if you don't find the objective you think is most important, please select other and add in the chat panel what you think should be our goal for SMAR studies.
So Atya, I'm just going to give people just a couple more seconds to respond. People are responding.
Okay, cool.
It's time to read everything, so I'm giving people an opportunity, and I'll share the poll results in just a few seconds. And I think you'll find that people have identified all of these as important things to as objectives. So, which is probably no surprise. So I'm going to share it right now so you can
Okay.
maybe just speak to the results, and you should be able
Cool.
to use the gray bar on the side to kind of go up and down to see it, but it's pretty evenly.
I should have had it an all of the above option. It looks like everybody is kind of equally spread between all of the topics. Maybe suitability for managed aquifer recharge says slightly. So the reason I asked was, and it's kind of a leading question. There we go, because all of these could be objectives for an isotope tracer study. You can use isotope tracers to look at subsurface resonance times. We can look at suitability for managed aquifer recharge, looking at groundwater ages. Some of the questions you want to ask for a study are more precise, like the resonance times, but sometimes the objective is more general, like understanding the groundwater system or understanding recharge mechanisms. So why am I so excited about using tracers? Well, they kind of integrate all the things that happen to our groundwater sample from the time it recharged all the way to the time it sampled, and everything along that groundwater flow path that happened to it may have impacted those tracer concentrations. Now, those tracers aren't really a detailed log of everything that happened to the parcel of water, but combining a number of traces we can use, we can glean something about recharge processes. We can glean something about resonance times, sources of water, and combined with more reactive constituents, we can learn more about geochemical processes along those flow paths. I don't think tracers are ever like this silver bullet. You just take one sample, you know everything. They're often part of a larger study with a lot of different lines of evidence, but tracers can be a prominent and powerful tool in that suite of tools that we have. So there are two different types of tracers. There are introduced tracers and there are environmental tracers or intrinsic tracers. They kind of speak for themselves. Introduced tracers are specifically added to a body of water, and then we try to trace that around in our groundwater system. Whereas the environmental tracers are naturally occurring. That means that they are there before we show up. That doesn't mean that they're natural. They can be anthropogenic constituents like CFCs or SF6, or carbon-14 or man-made isotopes, but we don't need to introduce them. The introduced tracers are often limited in scope in both space and time. We can only look at groundwater ages as long as we want to wait for the tracer to arrive. So we're typically looking at days to months, maybe a year of travel times. They're limited in their spatial domain because we can only tag so much water with the tracer, and we can't tag all the water recharges in the San Joaquin Valley. We can use environmental tracers for those large-scale applications. Of course, introduced tracers are more effort. We need to design the test, we need to introduce the test, and often we need to monitor a lot more often than when we look at environmental tracers. Usually environmental tracers, we go out once, or maybe I go out seasonally to survey wells, and then we send them back to the lab, or we bring them back to the lab and we analyze them. And as a result, usually introduced tracer studies have a higher cost, and most of that cost is the higher level of effort. You also get, I think, more valuable data out of it if we do it right. And the last thing I want to say is usually we can keep the tracer cost fairly small compared to the level of effort. The tracers we use are not cheap, but they're often just a few % of the total study budget. But if you look at environmental tracers, of course, the tracer comes free. It's just the analysis effort. So I make this distinction. First half of my talk is going to be about the introduced tracers. The second half about the environmental tracers. Come back to the right-hand side. Our #1 favorite tracer is xenon. Xenon is a noble gas, It's colorless, it's odorless, it's non-reactive, it's non-toxic, and it's not a greenhouse gas. It occurs naturally in nature, in the atmosphere. So there's a little bit of a background, but we can easily apply a lot of xenon to a water body to increase that concentration. And we've done that a number of times, and I'll show you the examples. And each time it's been really easy to get approval from the water boards and the Department of Water Resources, because it is this colorless, odorless, non-reactive, non-toxic, non-greenhouse gas substance that it's really hard to detect if we don't have the instrumentation that we have. We also like it because we've been able to develop some novel methods to inject it and to detect it. Now, we can, when we have, Livermore has, used xenon isotopes, so other noble gases for tracing groundwater. Those are really great if you have multiple sources of water and you want to do one tracer test and want to see where the different sources contribute to different wells. They require a lot of specialized analyses, so there is a higher cost associated to it, but it's been done. And the first example I'll show is one of those multi-isotope tracers. So this was in 2003, Brian Hudson led an experiment at Alameda County's Kaiser Pond, or Alameda County's, MAR facilities around Alameda Creek, including Kaiser Pond. Alameda County Water District has 2 rubber dams in Alameda Creek to back up the water to encourage recharge. So in 2003, they injected neon 22 in one pond, xenon 136 in Kaiser Pond, and xenon 124 in Bunting Pond, and that allowed them to monitor the arrival from the different ponds onto the Maury well fields here further in the south. But in 2011, the water board said, well, this is all great, but this is sort of niche, it's specialized, it's a lot of work, it's a lot of costs, these analyses. Is it possible to design a way to do that with xenon, or to develop a new tracer that is a lower cost? So we set out to do that. The goal was still to calculate subsurface residence times from surface water to drinking water, because it's a regulatory requirement. This time we focused on Kaiser Pond, which is 800 acre-feet pond. The flow distance to Maury Wellfield is about a quarter mile. And we used xenon, natural xenon, not an isotope, as the tracer. And we could demonstrate a new diffusion tubing injection method and also a new desktop instrument. So conceptually, we have a tank of xenon on the shore. We use this diffusion tubing, I'll show in a second. The xenon gets into the pond, it mixes around, but because it's a gas, it can still escape to the atmosphere. So we need to monitor the pond concentrations, and we did. Now, ideally, the water from the pond starts recharging the groundwater system, and it flows towards the monitoring wells and the production wells that are a little further down. So to get all that xenon into the pond, we want to make sure it doesn't bubble out and escape to the atmosphere right away. So instead of bubbling, we use this thin-walled silicone tubing, and we filled them with xenon, and we hooked them up to a cylinder. And that allows the xenon to diffuse through the walls of the tubing. But then, because that's fairly slow, it's able to dissolve. So we got a nearly 100% efficiency in xenon introduction. And using the 700 close to 800 liters of xenon, we were able to increase the background concentration 60-fold, which gives us a big dynamic range of detecting that water into these wells. So that's me trying to disentangle the tubing that we've prepared in the lab to roll out down into the pond. When Brian Hudson did the study, he used the traditional method of collecting copper tube samples for noble gas analysis and processed them in our traditional noble gas mass spectrometry lab, which involves cryogenically separating them using an isotope spike. It's a very precise and accurate procedure, but it takes about 1 hour for every sample. and it's limited to this manifold, so we can do about 9 samples per day. That's good, but it's not good enough for a tracer test because you need a lot more samples. You need to monitor the concentration of the xenon in the pond. So what we did is develop a desktop instrument. It's kind of cuts a few corners here and there, but because we're looking at larger gradients of xenon, we can get away with it. So it uses a membrane inlet, so it pulls the water in through a membrane, but then the water gets pulled out again, and only the gases can diffuse into the vacuum of the mass spec. We do all the processing online, on the fly, and then we send all the gases all together into a smaller mass spec. So we get almost real-time dissolved noble gas analyses. And in practice, we can do about 1 sample every 5 minutes. So we can do dozens of samples in a day. We also hooked it up to an auto sampler, so it's even more efficient. And the data we got from that is looks like this. The bond concentrations went up in the first 7 days that we introduced the tracer. And then because it's still a gas, it kept diffusing back to the atmosphere, so it decreased over the next 50 or so days. The xenon showed up in the first monitoring wells just after a few days. They were really close to they were on the bank of the pond. And it kind of lingered there, and concentration went down and then went up again. And all that time we waited for it to show up at the production wells. But it took about 130 days. And after 130 days, the lowest detection was about 5% above background, which represented less than 1% of the introduced of the pond water at the peak concentration. Concentrations in the production wells went up and then fluctuated quite a bit, and then kind of stayed around in the area for about 150 days. But in principle, we demonstrated that we can efficiently introduce the xenon and detect it at a pretty low cost and calculate groundwater travel times this way. A little while after that, I got a call from Ken Loy at West Coast. He said, "Can you do that same trick at an injection well?" And we said, "Sure, we can try." So West Coast was involved with, or was working for Woodland, the city of Woodland, who were developing an aquifer storage and recovery well. And West Coast was going to lead an injection and extraction test. And they thought it would be a good idea to add a tracer to get a better understanding of how the water moves in the subsurface, what the flow direction is, and which layer the water is injected in. Because the ASR well has 3 different screens at 3 different depths into 3 different confined aquifers. There's also a question of how much of the water mixes with the ambient groundwater. So during the 1-week injection, they injected 9 million gallons at about 1,000 gallons per minute. The flow paths were short to the monitoring wells, just about 200 feet to monitoring well 4. And this time we only used 5 liters of xenon because it's a much more contained, much smaller volume of water that we needed to tag. And so conceptually, it's you're injecting the water into the aquifer, and it becomes this expanding cylinder of injected water. And the question is this a perfect cylinder, or is it sort of moving half in one direction? Is there an isotropy that causes the injected water to arrive in a specific direction faster than another? And also how much mixing is going on around the edges of that injected cylinder. So on the ground, this is what that looked like. That's the well where the water was pumped down into. This time we didn't use the diffusion tubing. We dissolved the xenon at the lab into buckets of water that were lined with Mylar balloons. They look like party balloons because they are party balloons, because party balloons are very good at keeping helium inside, so they're also very good at keeping xenon inside. We used just a little bit of xenon, and we aimed for about 12 times background, and we got it pretty close to that. So these are the arrival breakthrough curves at the monitoring wells. Monitoring well 3C is closest, and it got hit pretty quickly. We asked their staff to sample every 2 hours because I was really afraid that we would kind of miss it in a way. Turned out we could have sampled fewer, but I felt it was better to be safe than sorry. It arrived at 4C a little later and at a much more gradually. So there was a lot of more either dispersion and mixing on its path to module well 4, or the plume isn't really a perfect cylinder and just moves slightly diagonally. One of the clear things that we saw was that there is no water arriving at monitoring well 3D, so it's not arriving at the deep layer, but it's mostly injected in the 375 to 490 foot aquifer. Now, after a 7-day injection period, they started pulling water out. And over the first 3 days or so, most of the water that got pulled out was the injected water. They continued pumping, and over the course of 14 days, they pumped out 3 times the volume of water that they injected, but practically all of the injected water. So the proportion of injected versus ambient groundwater changes. And the last 5 days, it was almost entirely ambient groundwater that was pumped up. So we're sort of halfway, and it's time for quiz number 2. The question is, which managed aquifer recharge mechanism are you most familiar with? And there it is. Cool. Gives me time to sip.
So while we're waiting for people to respond, this one is a single choice question of what is the most familiar with. So even though people are providing one response, they may have others that would contribute, but this gives you a different response than we saw in the previous one. So here, let me share the results.
Okay, that's interesting. Most of them are on-farm agricultural fields. So the reason I asked was that not all recharge methods are very suitable for gas tracers. Injection wells are closed contained systems. They have a well-defined recharge rate, so it's easy to design a tracer test. Recharge ponds are large volumes. Recharge rates are lower, but because it's a pond, there is loss to the atmosphere, but we can reasonably well predict that. So they're okay for gas tracers. Now, temporary spreading basins, on-farm agricultural fields, recharge is kind of intermittent. Recharge rates can be very high at first, but the water is fairly shallow and turbulent, so there's a lot of opportunity for the tracer to get lost to the atmosphere. And there's also an exchange of water with the vadose zone gases, possibly. So they're not as ideal. But it sounds like it's worth investing in tracers that may work as introduced tracers there. Fortunately, we have a suite of environmental tracers at our disposal as well. There are kind of 3 topics we can address with them. One is the source of the water, that we usually use stable isotopes, but sometimes salinity or ion chemistry is a very powerful tool for that source delineation. Travel times, there are a number of different isotopic tracers that are suitable for travel time determination on the time scale that we're looking at. There are more, but the other ones are usually at longer for older groundwater. And finally, we can look at dissolved noble gases to look at the recharge mechanisms. So the stable isotopes that we work on are isotopes of hydrogen and oxygen in water molecules. I'll show you the example of hydrogen. Hydrogen normally has one proton. That makes it hydrogen. Or sometimes it's called protium. It's the most abundant isotope. It has a mass of 1, and because it only has the one proton. Then deuterium is the one stable isotope of hydrogen. It has a neutron in the core, so it has a mass of 2, but because it only has one proton, it still behaves like a hydrogen atom or chemically. However, because it's slightly heavier than the protium atom, it can behave slightly different in a physical sense, in physical processes. So processes like evaporation, condensation. The deuterium is slightly more likely to be in the liquid phase or in the solid phase than it is in the gas phase. So as water vapor moves in from the ocean over land and it starts to condense, deuterium is slightly more likely to condense and rain out over the Central Valley, for example. As that storm moves further on over the Shiraz, it progressively has less and less deuterium in it. So we call it lighter and lighter and lighter because it has more of the light isotope in it. That trick works really well in California because if you look at the map of stable isotopes across the US, California has this really steep gradient between the low coastal areas and the high elevation Sierra Nevada. So we can use that to look at the different sources of water in a well sample. Hydrogen has a third isotope, and it's tritium. Tritium is radioactive at a 12.3-year half-life, but it's also incredibly rare. It has about, there are typically 10 to the power 18 more hydrogen isotopes than there are tritium isotopes. We have to go to great lengths to detect it. Tritium falls in a category of cosmogenic isotopes. These are isotopes that are produced in the upper atmosphere when cosmic rays interact with atmospheric gases like nitrogen and argon. Tritium gets produced if the neutron hits a nitrogen-14 atom, it gets kicked out, and then it combines with oxygen to form water molecules. So sulfur-35 and sodium-22 are produced if cosmic rays hit an argon atom, and the argon atom, core of the argon atom splits into in unequal parts. And then the sulfur reacts with oxygen to become sulfate, and sodium rains out as sodium ions. All three of them are incredibly rare. Tritium is even most abundant. There are typically about a few million atoms in 1 liter of precipitation. So we go to great lengths to detect them. So why do we bother? Well, these three isotopes have different half-lives, and the range of half-lives is really well suited for groundwater ages around MAR settings, where you expect groundwater ages in on timescales of months to a few years. Really, we expect them to be shorter than we can reliably calculate tritium alone. So that's why we've been investing in sulfur-35 and sodium-22. And Amanda Deinhardt and Richard Baby have been leading that effort, and they've been making some great progress. I have a few quick slides about the analyses. For sulfur-35, there's some chemistry involved in the lab to precipitate the sulfate, and then we can count it on a liquid scintillation counter, which is a kind of a nondescript Fritz-like object. But for sodium-22, we need a lot of water because it's so rare and because half-life is slightly longer than sulfur-35. We typically try to get about 500 to 1,000 liters of water. Now, it's impractical to bring that all back to the lab, so we bring out cation exchange resins into the field, process all the water through the resin, and then bring the resin column back to the lab. The chemistry is quite simple. We get the sodium off the column, and then we can count the sodium-22 on either a detector at Livermore in our basement, the Big 8, which is this massive 2-foot diameter, a lot of lead shielding around it to protect it from cosmogenic radiation that could give a background signal. But we've recently Amanda started collaborating with the Sanford Underground Research Facility in South Dakota, which is this mile deep mine. I think the mine is abandoned, and now they use it for physics experiments that need to be shielded from cosmic radiation. So these give us even higher precision measurements of sodium-22. Tritium helium dating is kind of a special case because it has both, we measure both the tritium as well as the decay product through helium. And with that, we kind of have this top and bottom half of the hourglass. And now we can calculate the age directly from that ratio and know. We don't need to know the input concentration. We can just, based off that ratio, we can calculate the age using that formula at the bottom. And I added in the number of blue tritium atoms in our hourglass and the 11 red helium-3 atoms, and I would calculate an age of about 17 years if that was the ratio. Tritium helium dating works on these big noble gas machines that I talked about before. We use copper tubes for the helium isotope sample because it's so diffusive that we need to absolutely make sure there's no atmospheric contamination. We use the same instrument for tritium analyses by containing the water in a vessel and then let the helium-3 accumulate. And then we measure the helium-3. Noble gases are also suitable for understanding recharge mechanisms because their solubility depends on temperature. We can look at the ratio of the noble gases and kind of reconstruct what temperature the recharge took place. Stephanie did a study for using sulfur-35 travel times at Orange County Water District MAR facilities. And based on the ratio between the activity in the basin and in groundwater wells, she calculated travel times in weeks of about somewhere between, some were very short, just a few weeks old, but typically there are between 20 and 30 weeks between the pond and the time they sampled it at the well. So the research ponds are about, the rates are about 800 acre feet per month. Flow paths are less than a kilometer, and it's used sulfur-35 as an environmental tracer. So it's a very similar scale to the xenon tracer, but this time they didn't introduce anything. We're working with UC Davis, Helen Dalka, and Laura Folia at the Casumnas on-farm field experiment, recharge experiment. We're trying to use the isotopes to understand infiltration processes, understand how much natural river recharge takes place, and get a better understanding of regional groundwater flow. So these are the more academic questions of trying to understand the groundwater system a little better. The on-farm flooding that happened last year was about 40 acre feet, and the flow paths that we're looking at are between 100 feet sort of on the farm itself to tens of kilometers in the regional groundwater system. We're throwing pretty much everything at it that we have there. I don't show any results of the cosmogenic tracers, but we have stable isotopes, tritium. We're trying to do tritium profiles in soils to see how fast the water moves through the unsaturated zone. And then using tritium, helium, and noble gases in groundwater to look at the regional flow. What we're finding is that there are variable infiltration sources, and there is some natural recharge from Deer Creek, which runs to the northwest of the fields. It's isotopically similar to local precipitation, but the recharge that takes place at much colder temperatures, which is sort of one line of evidence that this is Deer Creek water recharging rather than natural sort of diffuse infiltration of precipitation. On the other side of the fields, we find a lot of that Casumnas River water with a much lighter isotopic signature, more negative isotopic signature, and a range of groundwater ages between 4 years at Rooney Field to about 20, 35 years at Tykert. Now, if we zoom out a little bit, we're trying to use the regional groundwater sampling, both from the USGS shallow aquifer assessment, as well as the about 30 additional samples we collected south of the Casamigos River. Now we're looking at groundwater flow paths between 3 and some tens of kilometers with different the same suite of environmental tracers, stable isotopes, and tritium helium. And we're seeing that a lot of that Casamigos River water is limited to this sort of plume around the river, and we don't see it travel very far, either north or south. Most of it moves sort of to the south of the river, but it doesn't seem to get very far. Most of the ambient groundwater has recharged before the 1950s, so we don't find any tritium in these samples. So we know that the regional recharge rates are pretty low. We can also look at the whole San Joaquin Valley as the groundwater basin and compare, look at the
Hey, Orit, can you hear us?
I'm just checking. Yeah, I think we lost Ate. Let me see if I can just chat him to reconnect. Okay. Hopefully he can rejoin. Let's give him a minute.
Orit, while we have a possible break, I think we've got Adam on the line. Maybe he can tell us about the upcoming ISMAR next week.
Great idea.
Yes, hello everybody. Good afternoon. Yeah, ISMAR is next week starting on Monday. If you haven't signed up online, you can always register in person. It's in Long Beach, California. You can see the draft program on the ismar11.net website, and I'll put it in the chat. But also, we are going to live stream a portion of the event, so the entire day on Tuesday, as well as technical sessions on Wednesday and Thursday will be live streamed. So I'll send information about that as well. So if you can't be there in person, you can at least get some of the content live streamed. And then after the event is over, in a week or so, we'll post all of the recordings. So you can go in and get some of that content as well on your own after the event. But of course, we'd love to see you there, and it's always good to be in person. So if you have any questions, feel free to give me a call or contact me. Thank you.
Thanks, Adam. And I'm gonna email Ate to see if he can call in with the full link and phone number. Jenny, do you want to check on some of the comments, questions in the chat?
Yeah, it's pretty light right now. We have a question about using tracer analysis to validate groundwater models. And we've got a little bit of back and forth on that topic, but we don't have any other questions yet. So if folks do have questions for Ate and we get them back on the line, please feel free to add them in the chat. Otherwise, we could take this time. If anyone wants to suggest a future LunchMAR topic, anything that they're interested in, anything pressing. I know recently there were some drought executive orders that mentioned FloodMAR. I haven't had a chance to dive into them yet. But if someone is kind of steeped in them, it would be great, maybe and at the next LunchMAR, to have someone talk about the EOs and what they could mean for the broader FloodMAR community. I see Camiar's hand up.
Good, Camille.
Good afternoon, everyone. On that topic, Jenny, I would suggest, my understanding is that language in the drought executive order, and it's Articles 12 and 13 of the executive order, was crafted collaboratively between the Department of Water Resources and the Water Board. So I think they would be certainly part of that, getting the understanding of what the intent of those articles are. I really think the LunchMAR network can, or it would be helpful to look at that and see if it opens up some new opportunities over the coming year, particularly over the next wet season, to get things in order from a permitting standpoint, given that the executive order does provide provisions for waiving certain regulations as part of the drought emergency.
Thanks, Camille. And I see, Ata, you rejoined us. So
Yeah,
just checked in on other things in the meantime, but we'd love to be able to finish your presentation.
yeah, let's see if it's still, I can do share this one. I'm sorry, it looked like, and I don't know how long ago I lost you guys. Did I talk about the San Joaquin Valley before I lost you? Does this look familiar? Oh gosh.
You were
You were just on the Valley slide.
yeah, you
Oh,
were
okay.
you were just
This
starting
one.
your conversation about how the San Joaquin Valley could be considered one thing to look at.
Okay, so it wasn't too bad. I felt like I'd been talking for 5 minutes without noticing that I lost the connection. But yeah, so we've looked at using the priority basin gamma data. We looked at the stable isotopes and tritium of all wells across the San Joaquin Valley. And one of the great things about the priority basin data is that they did a lot of effort in making sure wells were representative spatially of the area, so we can lump them all together and say they all represent an equal weight across the valley. So we can do these mass balance calculations, and using the isotopes, we can calculate how much water in each well is river water or local precipitation recharge. And based on that calculation, we find that about 46% of San Joaquin Valley groundwater is river water recharge. Now, we can split out the wells that are modern, which contain tritium, from the wells that are pre-modern, which do not contain tritium. So if they recharge entirely before 1950s, there is no anthropogenic tritium in these wells. And the pre-modern samples contain a lot less of that river water. So combination of lowering water tables, river water irrigation, and also active managed aquifer recharge to increase the contribution of river water as a source of recharge in the San Joaquin Valley. We also see that river water tends to recharge at lower temperatures than local precipitation. So it has typically a recharge temperature below the mean annual air temperature. A lot of the wells have an isotopic signature that is somewhere in between river water and local precipitation. And these suggest to be a combination of either a mixing in the well or a river water irrigation that mixes with local precipitation. I have just a few more slides, and one is, Giovanni Castaldo worked with Thomas Harder and myself and Graham Fogg on looking at nitrate concentrations in domestic wells in the San Joaquin Valley. He compiled a data set of 370 domestic well analyses and looked at the same environmental tracers, stable isotopes, tritium, helium, and noble gases. And what he found is that the domestic wells that have predominantly river water have a much lower nitrate concentration than local recharge. And there are a number of hypothetical reasons for that. One is that irrigation with river water, of course, direct river water recharge is much lower in nitrate than anything you would expect from agricultural recharge. but also recharge with river water maybe at a higher rate, so it's more diluted than groundwater irrigation on agricultural fields. So there is an opportunity perhaps to focus managed aquifer recharge near communities whose wells have been threatened by both lowering water tables and water quality issues. Now, nitrate is just one aspect of water quality. There are many more that we should look at before we actually focus all our managed aquifer recharge on these communities. But this is at least a promising first step. The future research we're moving forward into is we have this groundwater age map. It has over 3,000 analyses across California, but we'd really like to even make it finer. It's hard to ask the state to do another 3,000 analyses. That was a multi-decade effort, multi-million-dollar effort as well. But what we can do is try to use machine learning algorithms to use auxiliary information about these wells to make prediction of groundwater ages in places where we haven't done isotopic analyses. So if we can refine the groundwater age map, I think it could be a useful tool to predict potential future MAR locations as well, based on the hypothesis that young groundwater ages at depth indicate conduits from the surface to the aquifer. So those are the places with high MAR potential because there is this connection to the deeper aquifer. And that's something we want to propose for internal funding for the next few years. And I'd welcome any thoughts and feedback on that topic to refine the scope of that study. That was my talk. We have a really nice website, water.lnnl.gov/isotopes, about all our isotope hydrology research. And that's part of the water.lnnl.gov website, which includes more fundamental research about water properties, climate science, some work on capacitive deionization. So all of the gamma reports and public reports we've produced are on our water.lnnl.gov isotopes, where you can find more about our personal pages as well. And with that, I'd like to thank you all for your attention and be happy to answer any questions you have.
Thanks, Asa. Great presentation, super informative. So we've got a couple questions in chat, and I'd also like to welcome folks online to raise their hand, turn on their camera to get into the queue to ask a question live. First question I see, do these isotopes, for example, xenon, change the resistivity of the local subsurface? Dominic's wondering if combining this technology with AEM or TOTEM has been considered.
Unmute. The concentration of xenon are so low that they don't change the physical or chemical properties of the water that you're traveling with. It's, the tracers are these chemicals or noble gases that are part of the process, but they don't really participate in the process. Yes, it has been considered to combine the isotope imaging with AEM or TOTEM. I think Greg Ulrich showed a little bit of that on a small field scale last month. Maybe his recording is still available. I really want to have a chat with Rosemary Knight about looking at more larger scale SkyTEM work, that AEM work that she's done to look at see if we can find correlations between where we see a lot of recharge or and high conductivity subsurfaces. Yeah, so.
Great, thanks. Another question in the chat. Have you done any studies using these isotope systems to characterize surface water, groundwater interactions in the opposite direction? So looking at quantifying groundwater contributions to GDEs, to groundwater dependent ecosystems.
Yes, Amanda Deinhardt, I'm not sure, maybe she's on the call today. She's working on a study in Shasta up in Shasta River, or north of, not Shasta River Basin, yeah. Looking at the isotopic composition of big springs and other springs in the area and wells. And to understand the time scale of groundwater flow paths towards those springs to see if they're, because those springs and groundwater dependent ecosystems are obviously groundwater fed, and what the time scale is of the climate risk. There are additional isotopes that we can use in surface water. Radon is an isotope that's produced in the subsurface, so you find it in surface water where there is a groundwater influx. We've done some of those studies in Martis Valley, so we have a paper out that's on our website looking at groundwater streamwater interactions in Martis Valley.
Great, thanks. And your website is linked in the chat as well. I think we've got time for one more question. You mentioned that xenon is not the best tracer for on-farm recharge. What do you recommend is the best tracer for AgMAR?
That's a hard question. I don't know. Xenon is not the best, but from a more academic standpoint, I think it would be really worthwhile trying it because it might help us understand how much exchange there is with the subsurface soil gas. It might tell us a little bit about how much of the recharge is sort of diffuse through all the partially filled pores, or if there are these dedicated flow paths of high saturation where the xenon is contained. I probably want to pair it up with another gas tracer that has different gas properties. There are other options if you're in a system where you're not worried about drinking water protection. Your options are, may have more options of solutes that you could add, or dye tracers. We've looked at the cost of stable isotopes like deuterium, but that they're really expensive really quickly. So I think 1 acre foot was about $20,000. So that kind of cooled our interest in stable isotopes. You could do it on a much smaller scale, of course, and get a lot of valuable information about short flow paths. But for on-farm recharge, I think the natural contrast between or the environmental tracers is valuable, but I'll keep thinking about introduced tracers on that scale. Thanks.
Thank you. All right, well, a little after 1:30 now. Appreciate your time. Also, that was a great presentation. I invite everyone to give us a virtual high five or applause, and appreciate your time. And we'll see everybody at the May LunchMAR.
Cool. Thanks, everyone.
Thanks all.
Thank you.
Thank you. Thanks,
Bye.
Sata.